Hello everybody, I'm Peter Stuttard and I'm your presenter for this short module. The module has been prepared on behalf of the Pierian Academy, which in its turn is an initiative of the Team Pierian. And there are some contact details and a web address, URL for the Pierian Academy on the last slide if you want any more information. However, in this module we're going to basically ask two simple questions, or answer two simple questions. Namely, what is Integrated Logistic Support, ILS, or Integrated Product Support if you prefer, and why is it so important that we do ILS and that we do it well? The answers are fundamental. They will provide us with a solid, robust basis on which to found our understanding of all things ILS. And understanding ILS is very, very important. There is a lot of misunderstanding, an awful lot of misconceptions associated with the topic of ILS. Misunderstandings and misconceptions that can ultimately lead to the fielding of weapon systems which have extremely high, often unaffordable through life cost, and very poor operational availability. And that leads ultimately to constrained operational capability, which is of course very important. So what is ILS? The last refuge of the charlatan. Also it has been described. And given some of the ILS programs that I've witnessed, I can understand some of the cynicism that exists in the marketplace with regards to ILS. But there are many standards that make a serious attempt to define ILS and to define the ILS methodology. But whether they succeed or not is open to debate. Many of the attempts to define ILS fail, as many ILS programs fail, because, in part at least, they don't apply the fundamental principles that underpin the ILS concept. So perhaps it's better to resort to first principles, to go back to basics, rather than attempting to define ILS by reference to standard specifications and textbooks, etc. And that's really what this module is going to attempt to do. We're going to take an alternative approach and ask what ILS should be, and then hopefully any fundamental principles will not only be revealed, but they will become self-evident, unarguable, hopefully. We're going to start the process by asking some basic questions. It can be a salutary process to ask what apparently dumb questions, and questions such as, what do we mean by integrated when we say integrated logistic support or integrated product support? What precisely is it that we're integrating? And what precisely is logistic support or product support? Similarly, we may ask the question, what is logistic support analysis or product support analysis? And in a similar vein, what is the actual product of an ILS program? What precisely is it that we are making when we run an ILS program? Now, I'm stressing the need for these answers to be precise, because it's all too easy to come up with vague and ambiguous answers to these questions, answers which are subject to a range of different interpretations. So let's have a go at this. Let's approach the problem in a logical and structured manner, and let's apply a good old-fashioned dollop of common sense. We can start with a very simple statement, that the output, the product of an ILS program is a support solution. We'll decide what a support solution is shortly. So the aim of an ILS program is to develop and then to maintain an optimal support solution. That support solution should be developed and maintained by applying the most logical, practicable, most cost-effective methodology that it is within our powers to define. Now, I think these statements are uncontentious. They are axiomatic, so we can develop our argument from this point of reference. And note that we need to optimize two things. We need to optimize the support solution and the methodology by which that solution is developed. In other words, we need to optimize the product of ILS and the ILS process. An optimal ILS product will be a support solution that delivers the maximum operational capability at an acceptable and an affordable through life cost. But note also that 2, 3 and 4-star generals from our armed forces are also asking for flexible, agile and dynamic and adaptable support solutions. They want greater support velocity, greater support precision, and the ability to fight hurt and greater visibility. Now, discussing what each of these statements means is a task for another day. But I think what we can agree is that what the commands want, that what they need is an improved standard of engineering support. They want a better support solution. And once we achieve all of this, of course, we have to sustain it throughout the life of the system. And all of this has to be delivered with limited finances and limited resources. The customer ultimately, though, needs a cost-effective support solution where cost is defined in through-life cost terms and effect in operational effect terms. Our support solution needs to deliver a support advantage to our armed forces, an advantage that is over the enemy. Now, of course, all we need to do is define a support solution. To do this, we're going to start not at the beginning but at the end. We're going to consider an engineer supporting a complex piece of equipment in a combat environment, in a war zone. Now, on this diagram, the bad guys are over to the right hand side and the good guys are over to the left. From this perspective, defining a support solution is relatively simple. Let's start with the kit, the platform that needs supporting. If we are going to support a piece of complex military equipment, the mission system, then that mission system needs to be designed so as to be supportable. That is, we must design for support. The mission system should be reliable, durable and robust, maintainable, testable and upgradable. We need to take account of factors in the design such as standardization across the design, across a family of designs and so on. We need to look at systems architecture and the level of risk associated with the resources which are embedded in that system. We need to design the system so it enables condition monitoring and usage monitoring. We need to take account of factors such as maintenance age, which can be complex like built-in test equipment, or very simple like steps to allow access to different parts of the system. We need to make it safe and operable, and we need to make sure it's disposable at the end of its life. Now, an ILS program has to optimize and to achieve the right balance between all of these aspects of the mission system design. And it has to do this within constraints, given constraints such as time, cost, design freedom, technical feasibility, and so on. Now, this is the first component of our support solution. Then we have to consider what we will need in order to support this mission system when it fails, as it will. And we were going to need a lot of stuff. We're going to need people, that's maintainers, drivers, suppliers, etc. We're going to need spares, consumables, test equipment, tools. We're going to need a lot of information, maintenance manuals, parts catalogues and operator manuals, as well as facilities, transport, packaging, handling systems and storage. We're going to need information management systems as well, which are not shown on this slide. But plainly, this is not enough. Resources on their own will not meet the need. We also need systems, organisations and processes to move, to deliver, to repair, to recover, to update, to resupply, to train and to retrain personnel. And then these processes will need additional processes. For example, we'll need training materials, classrooms, training aids and teachers. i.e. we will need a support infrastructure that will get the right stuff, the right resources, in the right place, in the right quantities, in the right condition at the right time. And this support infrastructure will be complex. It may be very, very complex. It is a system in its own right, which we will call the support system. And this is the second component of our support solution. And whilst I've been using land systems to illustrate the concept here, of course, this applies equally to maritime and to the air environment as well. I think it is self-evident that the support system must complement the mission system, and this is generally well recognised and accepted. Less well recognised is the need for the support system to take account of the manner and the environment in which the mission system is operated and supported. Now, we're going to call the operating and support environment the employment plan. And support engineering needs to take account of a range of employment plan characteristics, including, but definitely not limited to, the need to sustain operations during the performance of a succession of operational tasks. That is, we need to sustain the platforms, come what may, during a wartime combat type scenario. We also need to take account of the physical environment as it affects the mission system and the support system. Particularly, we must take cognizance of the lines of communication. How long are they? How vulnerable are they? What impact will this have on our support solution? For example, consider when we're doing spares analysis, are we taking account of the impact of enemy action on the lines of communication? They may cut the lines of communication, or they may simply constrain them. And if we're not taking that into account, why not? Because that will determine to a degree how many spares, engineering spares, we need to carry with us in theatre. And that leads us on to consider the nature of and the impact of enemy action more generally. For example, what types of battle damage are we expecting? Because we have to carry out battle damage repair. What is the level of attrition we're going to expect on our support resources, and have we taken that into account during our planning? Consider also that modern operations will almost certainly require our operational and our support assets to be dispersed over a wide geographical area for their own safety, and this will increase the support challenge. And the employment plan, of course, must also take cognizance of the support system, its capabilities and its limitations. The first principles are now becoming apparent. The key takeaway being that we need to take a systems approach to support engineering. Our support solution can be described in systems terms. The support solution is comprised of the support aspects of the mission system design, the support system, and key elements of the employment plan. And each, of course, should be optimal within its own right, but also collectively they must form a coherent, integrated optimal system, the total system. It is this system and the interactions between its elements that determine both through-life cost and operational capability. So far, we have considered the product of ILS, that is, the support solution. We know what it is now and why it is needed. What we must now consider is how this support solution is developed. We have to consider the process or the processes that will be required if we are to develop an optimal support solution. And given that support solutions are, even relatively simple ones, are complex systems, and returning to our starting point, it is evident that we need to adopt a highly structured approach if we are to succeed, if we are to produce a support solution that is anywhere near optimal. To manage something as complex as a support system, a support solution, we need to employ systems engineering concepts. Systems engineering being an approach which is specifically designed to address high levels of engineering complexity. Systems engineering requires us to set requirements for and to design the mission system, the support system, and the employment plan concurrently. It requires us to implement incremental and spiral development strategies. It requires us to make extensive use of in-service feedback and historical data. And now, to achieve this, to achieve systems engineering, we need to use tools which will facilitate our understanding of complex system dynamics, tools that allow us to predict and to monitor the behaviour of complex systems. Now, there is a wide range of tools and techniques available to the ILS fraternity. Such tools include sophisticated tools for developing, presenting and managing training and technical documentation, advanced and ever more affordable test and sensor technologies, complex system models, for example agent-based simulation tools, tools that automate data gathering, and information and analysis tools and techniques such as text analytics and artificial intelligence, to name just a few. But noting that feedback and optimization techniques lie at the very, very core of the ILS and LSA process. We also have to recognise, however, that there are a great many different support engineering disciplines: reliability, maintainability, testability engineering, technical publications, training, provisioning, etc., etc. And it is essential that we define a coherent, overarching support engineering process if we're to avoid nugatory effort and to minimise divergence between the different outputs of those disciplines. For example, many disciplines make use of failure modes, effects and criticality analysis, FMECA, or failure modes and effects analysis, FMEA. Each discipline has their own priorities, and each therefore may have a slightly different approach. Approaches which may take place at different times, using different tools and recording into different locations. The effective ILS, however, requires that a common FAMICA is performed in an iterative manner and in a manner which satisfies the requirements of all the members of the engineering community. That is the reliability and maintainability engineers, the reliability and maintenance analysts, the safety engineers, etc. ILS requires a common FAMICA that satisfies all the needs in a timely manner. Besides FAMICA, however, there are a great many other potential overlaps and duplications that we could eliminate, such as the overlap between the training and technical publications discipline. Now this is a fundamental principle that underpins the concept of ILS and LSA in particular, logistic support analysis. That is, wherever possible, a single set of activities, a single set of analyses should be performed, eliminating duplication and preventing divergence. This approach facilitates and is facilitated by the use of a common data and information sets. Hence, an effective ILS methodology replaces a range of disparate activities and analyses with a coherent common approach facilitated by a single underlying information and data set. And the R&M engineer, the RCM analyst, the technical authors, provisioning people, the training specialists, etc., they all apply their skills to the relevant elements of this common integrated process. These then are the principles that define ILS and LSA programs. In summary, if we review the argument above, we can identify 6 categories of integration that we would need to address if we were to implement an effective ILS program. They are: number 1, the mission system design must take cognizance of the probable operational environments, the terrain, the length of the line's communication, the physical environment, enemy action, etc. 2, the support system design, that is the support infrastructure, also needs to take cognizance of the probable operational environment, the terrain, the length of the line's communication, the physical environment, enemy action, etc. 3, the support aspects of the mission system design need to be considered as a whole. They include things like systems architecture, the ability to conduct battle damage repair, upgradability, standardization, human factors, the use of low risk resources, including but not limited to obsolescence management, as well as durability, robustness, reliability, maintainability, testability, etc. 4, similarly, the elements of the support system design also have to be regarded as a whole. This is why we refer to it as a support system. All the processes, the organisations, the infrastructure, the resources that comprise the support system should be complementary and optimised as far as possible, as far as is practicable. 5, the support system has to complement the mission system and vice versa. And finally, number 6, the processes by which the 5 aims above are achieved, the ILS or support engineering processes, should be coherent and optimal. Nugatory effort and omission should be eliminated. To conclude, poorly implemented ILS programs often reduce the level of integration. They introduce ILS processes which run in parallel with, rather than replacing, those of the individual support disciplines. They reduce program efficiency and they drive in cost. Such programs squander the very significant benefits that could accrue if a genuinely integrated set of processes was applied. And they are the reason why ILS has gained something of a negative reputation in some areas. Real ILS is a series of optimal, highly integrated processes where nugatory effort has been eliminated, where there are no omissions. ILS processes utilise common information sets. They employ systems thinking and systems engineering techniques. They capitalise on available technologies and techniques to develop highly integrated and coherent support solutions, solutions which are optimal within the given constraints. ILS is the most logical, most practicable, most cost-effective methodology by which an optimal support solution can be developed. And if your ILS program doesn't fit that description, then you need to implement an alternative approach. That's all, thank you. That concludes the presentation. If you have any feedback or comments or questions, please contact me at the email address above, or alternatively, you can visit the Pierian Academy website for more information. Thank you and goodbye.